So welcome to Math317 Operations Research. This is lecture 6. Today we're going to talk about canonical forms. We're going to talk about how do you write something in a standard notation. This turns out to be tremendously valuable. And the reason is if you are able to do this, then rather than saying, well, if it's written like this, do this, if it's written like this, do this, if it's written like this, do this, you just have one way to read things in. Now, sometimes when you're writing programs, you might want to take advantage and exploit the fact that the problem has some additional properties. And so if you try to always put it into canonical form, it may not be the nicest thing to do. But in terms of theory, when you're trying to prove something about the properties of a system, it's often very nice to be able to do this, because then you know when I'm reasoning, I know it has this form. So one of the things we're going to be doing is we'll show that any linear programming problem can be written in a certain form, and then we only have to analyze problems of that form. It may be a bad idea to put something in this form. It's going to cost you potentially some variables. And so if you're trying to do things efficiently, it may not be the best decision. But if you're trying to analyze things, it's really nice to know that we can start off with something in that form. So I want to start off with something that should hopefully be very similar to things you've seen before. Solving equations. All right. How many of you have taken abstract algebra? Okay. My hand is down. I have never taken abstract algebra. I've taught it. I have not taken it. All right. You learn about solving equations. Let's start off with the easiest one. X plus c equals 0. All right? I'm going to assume that this is not that hard to solve. Right? And the solution, not surprisingly, is x equals negative c. We can make this a little bit more interesting. Bx plus c equals 0. Again, this is not going to be that hard. This will just be x equals negative c over b. All right, linear equations are not too bad. I will assume when I'm writing something like this that b is not 0, that the coefficient of the highest degree is always non-zero. Let's start looking at quadratics. What's the easiest quadratic to study that I'll allow you to study?
X squared.
X squared.
Equals constant.
Okay, so I'll try to write this in from x squared plus c equals 0. Now, I'm not going to solve x squared equals 0. That's just too much even for me. But x squared equals c, sure. And then you'll get x equals plus or minus the square root of c. So the idea is I can solve this without too much trouble. If I gave you ax squared plus c equals 0, what a shock, you'll get x is equal to plus or minus the square root of c over a. That's not going to be a problem at all.
Yes.
Did I make a mistake? Oh, yeah, there should be a negative c, yes. Thank you. So the idea is if I give you a general polynomial now, I want to reduce it to something like this. So if I give you ax squared plus bx plus c equals 0, I want to write this as maybe alpha y squared plus beta equals 0. And if I can write it like this, then I can solve it by using the method I've just developed over here. So I'm assuming everybody has seen the quadratic formula numerous times. How many of you are comfortable proving it if you had to right now? This one I will raise my hand for. Okay, so the quadratic formula is one of the big results we have. Where does it come from? Well, one way to prove it is if you know the answer. This is the method of divine inspiration. And then you can just write down and just explicitly show that when you expand out x minus root 1 times x minus root 2, multiply that by a, you get the right thing. But it's nice to see where things come from, and it comes from completing the squares. And this is the power of writing things in a good form. So if I give you ax squared plus bx plus c, this is the same as x squared plus b over ax equals negative c. I'll put the c over on the other side. And I want this whole thing to be some nice thing squared. And you can see this is beginning to look like ax plus h squared, which would be ax squared plus 2hx plus h squared. Uh-oh, couldn't find upload video. Okay, so what should we take H to be? B over 2a. And then H squared will be B squared over 4a squared. And now what we do is we do nothing. Right? There are two ways to do nothing in mathematics. What are the two ways to do nothing? Add 0 and multiply by 1. We're going to add 0 here, so this is going to be the same as a x squared plus b over ax plus b squared over 4a squared minus b squared over 4a squared equals negative c. And so this is then going to become ax plus b over 2a squared, and then we'll have a minus b squared over 4a. So when we bring it over to the other side, we'll have b squared over 4a minus c, which is b squared minus 4ac all over 4a. I divide by the a, take the square root, subtract the negative b over 2a, and after a little bit of algebra, you'll get x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And this is one way to see where the quadratic formula comes from. It comes from completing the square. It comes from trying to reduce a generic quadratic to a very simple quadratic that we can do. We can solve quadratics that don't have a middle term very easily. It's not that much harder than solving the linear equation. This is what I'm trying to do in the classes. I'm trying to motivate the thinking process that goes into a lot of the analysis. Take a simple problem that you can understand and then move the more complicated thing to that form. Now, building on our success on the quadratic, where should we go next? The cubic. And there is a way to solve this. And I think it's actually called the depressed cubic. I know it sounds sad, but you remove the x squared term and you get something that you can work. And then building on the success of the depressed cubic and the cubic, we move on to the quartic. And unfortunately, what happens is the method that you use that creates other equations to look at, once you get to degree 5 and higher, it actually creates a polynomial degree larger than what you started with. So when you're doing all of this stuff, you're eventually reducing things to simpler problems. If you want, you could even look at it at this point as this is now a linear equation in x plus b over 2a squared. Because if I can solve that, I can take a square root. So unfortunately, we can't keep pushing this forward and forward and forward, but we can push this for a while. In the old days, when people used to solve quadratics and equations like this, they did not really like minus signs. They wanted to view things as geometric objects. So depending on what you had, you would have all these different forms of a quadratic. So you would have a couple of positive terms equals a couple of positive terms. You would never have 2x squared minus 3x plus 5. You would have 2x squared plus 5 equals, and then the other term there. And you would have different methods to solve each one of these. Okay, we all agree now with our great algebra skills, let's just solve them all together, let's just unify the approach. And that's what we're going to be doing now for linear programming. All right, any questions about this? All right, so the next thing is, how do we write matrices? What kind of forms can we do for a matrix? So eventually we will not be looking at square matrices. We will be looking at underdetermined systems, but let's start off with square matrices. Linear algebra is a prereq for the course. We're not going to do too much with it, but let's review a little bit. All right, so let's say A is n by n. What would be a nice property for an n by n matrix to have for us? So that we could really analyze it.
It's diagonal.
Diagonal, okay, that's really good, but sure. All right, so if A is diagonal, we're done. That's a really good form. So in fact, the question is, when is a matrix diagonalizable? When can I convert it to diagonal? And diagonal essentially means if you choose the right coordinate system, the transformation is really nice. It's just rescaling in each of the perpendicular directions. So what other matrices could be diagonalized?
Invertible.
Not every invertible matrix can be diagonalized. So I can give you the matrix 1, 1, 0, 1. This matrix is not invertible, but it cannot be diagonalized. Yes?
A real symmetric.
Real symmetric. So we have a big theorem. A real symmetric implies there exists an orthogonal Q such that either QA, Q transpose, or Q transpose AQ is diagonal. I always forget which way it wants to be. So, yes?
What's a real symmetric?
So a real symmetric matrix means that all the entries are real, and each row is perpendicular to all the other rows. And each row has unit length. So when I take the transpose, a row becomes a column. And so when I do the dot product, row I dotted with column J of Q transpose is 1 if I equals J and 0 otherwise. So this is telling us that if your matrix is real symmetric, if you change your coordinate system, then in this new coordinate system, your matrix is diagonalizable, and that's easy to analyze. So if we wanted to study real symmetric matrices, it's sufficient if we're only looking at one matrix to study a diagonal matrix if we can change our coordinate system. Not every matrix is diagonalizable, however. What could you do, though, to an arbitrary matrix? Yes?
Can you just add zeros and try to transform it to a way that could be diagonalizable afterwards?
So, but you've got to be careful that you can't change the transformation. So you can change your coordinate axes, but you can't change the transformation itself. It will look different depending on the coordinate system you look at. If you measure something in yards or inches or meters or furlongs, you will get different numbers, but the physical quantity is the same. So the numbers can change depending on what system of measurement I use. But the actual physics can't change. So this is an extremely important point from linear algebra. All right. There are a lot of very bad units. You know, my physics textbook in high school had the conversion factor between meters per second and furlongs per fortnight. You know, the only place I can ever think where you might use a furlong per fortnight is a slow construction project. You know, the parking lot is expanding at so many furlongs per fortnight. Okay, this is not a unit of measurement you want, but you could use it. The most general form, well, there's really two types of things you can do. You can always put a matrix into upper triangular form. And when you're trying to do things like Gauss-Jordan and whatnot, you want to reduce a matrix to a convenient form for a lot of calculations. So we can upper triangulize. What else do you think you could probably do if you could upper triangulize an arbitrary matrix? You could what? You could, but we would never, ever do that in this class, right? It's like putting the jelly on top of a peanut butter jelly sandwich. Is that the right way or the wrong way? I won't say which way is right or wrong. Right? Does it really matter? But it's nice if everybody does things the same way. How many people are taking economics? Or have taken economics? What did I just draw? Okay, what's the x-axis? And the y-axis? Which is the supply curve? This one? Yes, the more money you have, the more you're willing to supply, and this is the demand curve, the more it costs, the less you're... Did I draw it right? Yes, yes. I'm sorry. Right. Well, this is an advanced class. This is 300 levels, so I'm giving them a little bit of a curve. Do you have to have $ your price here and quantity here? No, there was somebody who asked that in my freshman economics class. You can change them. Should you change them? No, because then if you do that, God help you, you've got to now think every time you look, well, that's not necessarily bad economics. You have to think every time you look at a text now, which convention have they used? It's really nice if everybody uses the same convention. This is the idea of the canonical choice. We're always going to do it this way. It makes it much easier to just glance down and see what's going on. So an arbitrary matrix can always be put into upper triangular form. There's also Jordan blocks, where an arbitrary matrix can be put into blocks of the following form. Lambda 1, lambda 1, 1's down here, 0's everywhere else. And then the next block is lambda 2's with some multiplicities, and 0's everywhere else. And these are just the most general form you can put a matrix in. And for a lot of problems, it's nice if you have a clear, convenient form. It simplifies a lot of the computations. Not every matrix is diagonalizable. There are some matrices, unfortunately, that cannot be put into a diagonal form. I gave you an example earlier, the matrix 1, 1, 0, 1. There is no way to diagonalize that. There are matrices that have real entries that don't have all real eigenvalues. One of my favorite is the matrix 0, negative 1, 1, 0. This is either rotating by 90 degrees the vector or rotating your axes by 90 degrees, depending on whether or not you want to be a physicist or a mathematician. And it depends on where you put the minus sign. You can't understand this only looking at the real numbers. Because if you rotate your vector by 90 degrees, there's no way to have a real eigenvector, because the direction has changed. The only way you can have one is to work in the complex plane. We're not going to go too much into that, but I just want to give you one fun example of a problem which cannot be diagonalized, but it can be Jordanized, and that is enough for a lot of the analysis. The problem comes from John Conway, who is a phenomenal source for interesting mathematics. If you've ever seen The Game of Life, where these cellular automata, he's the one behind this. So I'm not going to say what the sequence is called yet, because that would give it away. I will give you terms of the sequence. If you've seen this before, you're not allowed to play. Tell me what the next term in the sequence is. Anybody seeing it? What's the next line?
1, 2, 2, 1, 2, 2, 1, 1.
Wait, 1, 2, 2, 1.
1, 2, 2, 1, 2, 2, 1, 1.
What's the first line? What's the second line?
1, 1.
1, 1. What's the next line? 2 1s. 1, 2, 1, 1.
The fourth line should be.
Did I make a mistake in the fourth line?
Fourth line.
I have 1, 1.
Fourth line. Math fourth.
This one?
Yeah.
1, 2, 1, 1. Yeah.
Oh, yeah, sorry. It's 1, 2, 1, 1. Sorry, yes. So 1, 2, 1, 1. So the next line would then be 1, 1, 1, 2, 2, 1. 3, 1. And then, so hopefully we've done it correctly this time. So this is either called the see and say, or some people say the look and say. It turns out that there's a way to associate 92 elements to terms in this. 2, 2 is helium. There's the cosmological theorem that says from some point onward, every one of the 92 elements is going to occur in every line. You can talk about the growth rate from line to line. It turns out it's the largest eigenvalue of a 72 by 72 Jordan block, because the associated thing is not diagonalizable, but is only Jordanizable. The original proof was lost in Conway's office, and as a grad student who was once paid to try to clean up one of his offices, I can easily believe about this getting lost. He and one of his students had to reprove it another way. Fascinating, fascinating problem. And it's just an interesting way of seeing how you can start off with something that seems completely silly, but it leads to good mathematics. And it leads to something which is not diagonalizable. So we cannot always assume that things are diagonalizable. Now, with probability 1, however, if I tweak the matrix just a little bit, it will be diagonalizable. So if all of the eigenvalues of the matrix are distinct, then the matrix is diagonalizable. It's extremely rare in a probability sense to have a repeated eigenvalue. There might be some physical grounds why that happens, but if you're looking at a generic thing, if we tweak it by just a little bit, we're normally fine. And in fact, that's going to happen later on when we're doing our linear programming, that there'll be certain times where we will have this little bit of an assumption that we want to make sure we are not in a degenerate subspace. The probability that you're in a degenerate subspace is 0. If it happens, a small little tweak. What you hope is that you're not in such a position that you are so sensitive to these little tweaks that you have wildly different solutions. For a lot of continuous problems, it's fine. For discrete problems, however, small changes can have tremendous impact. Right. One of the greatest examples is getting tenure at Williams or at any school. This is a 0-1 decision. And if one of my wife's friends years ago wanted to be the person that would take the committee 3 days to a week of hard deliberation before they finally return tenure. To know that they spent exactly the right amount of time on their academics. Is this a good strategy? What's the danger of the strategy? For those of you who are considering a career in academics, you need to learn the danger of the strategy very fast. If you just miss, there is a tremendous change in the result. It's nice when you have a system that is not so sensitive. So whenever you're doing a problem, you always want to get a sense of what really depends, what has the biggest impact. All right, so these are different canonical forms. What I want to do now that we've seen this is talk about the canonical linear programming problem. So, canonical linear programming problem. So we'll assume each xi is greater than or equal to 0. We'll assume ax equals b. And we will minimize C transpose x. I will try to put arrows over things to let you know that they're vectors with many components. Right. We will always assume a linear programming problem can be put into this form. So this is the canonical formulation. So that must mean there must be other options. What could we do maybe instead of all the xi greater than or equal to 0? What else could we look at? Yeah.
Negative values.
They could be negative values. We could have the xi's be real. Now, in some sense, you might say, well, look, any problem with studying in the universe should have some physical grounds on it. Anything that's physical, I can't be below a certain magnitude. Maybe it's 2 to the negative 2 quadrillion factorial. And I can just write everything as 2 to the negative quadrillion factorial plus a non-negative amount. Just shift everything over like that. But theoretically, for some math problems, we actually do need to allow things to be any real number. So while on physical grounds, we might be able to have an absolute lower bound, for theoretical reasons, for some of the problems we want to look at, we do want to allow any real number. All right, so that's one thing that we might want to change. What about 2? Instead of having equals 0, what could we have?
Component twice larger or equal.
Yeah, so some of the components might be greater than, and some of them might be less than. And the last one, instead of minimizing, what could we do instead of minimizing? Maximizing. So what we want to show is that you give me any of these tweaks, and I can very easily get it to be looking like this. The question?
Yeah, I have a question. So like when we're doing linear programming, is x sub I a coefficient?
The x sub I are your choices. These are the things you're choosing. So if you want, in the diet problem, we have two types of food. And xi is how much of food I you have. And then the matrix A will give you, say, the nutrient values of the different food items. And then C will give you the cost of the different things. So which do you think is the easiest one to adjust? 1, 2, or 3?
2, right? Because it's the food that you choose.
Well, with 2, we have to be able to deal with greater than or less than. For 3, we have to either do a minimum or a maximum. If you can minimize, can you maximize? How do you pass from a minimum to a maximum?
Negative.
Yeah, negative. So 3. If we want to maximize C transpose X, it's the same as minimize negative C transpose X. I never said the coefficients of C have to be non-negative. C is our cost function. So going from a maximum to minimum is not a problem. And then in calculus, you've hopefully learned different tools and techniques to find some of these. This is the Lagrange multipliers, this is critical points. There's a funny story which is almost surely false, that when they were building the stealth bomber and the stealth fighter, they were searching to maximize stealthiness. And they didn't check to see if they were at a maximum or a minimum. And according to the story, they built the I'm here plane. Almost surely not true, but I like to imagine somebody not checking the second derivative or something like that. And yeah, we thought it was a little strange that we were putting loudspeakers on it, but... All right, so point 3 is easy to deal with. How do we deal with points 1 and 2? Those ones take a little bit more work. So, dealing with 1. So case 1, let's assume xi is greater than or equal to some number t. We have some kind of bound like this. Change variable. Let yi equal xi minus 2. Now we get yi is greater than or equal to 0. So wherever I see an xi, I just replace it with yi plus t. So replace xi with yi plus t. And if you think about what are going to be the consequences of this, well, if I go back into the equation here, that's going to just change each row over here. It's going to just shift the values of b on this side. And over here in the cost function, it's going to just add a fixed amount. You're basically t times the ith component of c. So it's going to change the cost by a constant amount. It's going to just change the value of b here. As long as I can do this for an arbitrary b, I can still do this. So it's not a big deal at all. If I had some conditions on b, then we would be in trouble. And that's why you always want to be careful. Well, where am I assuming structure? Once I assume structure about the x's, I have to let b and c be arbitrary, because the things I do are going to affect b and c. So this is what would happen if x is greater than or equal to some number. Case 2, if x is just an arbitrary real number, xi is an arbitrary real number, let xi equal yi minus zi. So this is a really nice trick. You give me any real number, and I can write it as a difference of two real numbers, and here, yi and zi will both be greater than or equal to 0. Is there a unique choice of yi and zi if we're given xi? No, right? I can add the same amount to both. This should remind you almost of like the fundamental theme of calculus. There's not a unique antiderivative. Doesn't matter. When we use the fundamental theorem of calculus to find areas, we're always looking at f of b minus f of a. So if we shift the antiderivative by a fixed constant, it doesn't make a difference. It's going to cancel out. So there is no unique choice of yi and zi, but that's fine. We can replace any real variable with two positive variables, or two non-negative variables. This may be a bad thing to do because you're now introducing more variables. All right. But it at least allows us to always assume that our variables are non-negative. So the last one is the fact that we want to assume that we only have equality. So let's look at one of the equations. Let's say we have ai1 x1 plus ain xn is greater than bi. Something coming from the ith row. We want to have equality. What we can do to get equality is we can just add another variable. Right? If this is greater, I would subtract something. If it was less, I would add something. And so I can figure out what to put in depending on whether or not I have a greater than or a less than. And I can always do it in such a way that I'm putting in something that's non-negative. So here, I could add maybe negative zi. And so if this was a little bit larger, we'll be fine. So again, we can convert things to a nicer form or a standard form, but there's a cost. And what you have to ask is, would it be better to write a specialized did I do things the wrong way?
Basically, just defining zi and the difference between the two.
Right, is I'm going to put in a new thing over here. So now I would look at ai1 x1 plus ain xn minus zi now equals bi. So these would take on their values as before. And then the zi is the slack I need to subtract off a little bit of this to make this bi. Does the zi enter the cost function? No, I don't change the cost function. So it's not the case that every variable has to be playing a prominent role in the cost. But I can adjust this and make it a strict equality by saying, look, if it's larger than bi, just subtract a little bit to make it equal to bi, and then don't worry about the value. If the value doesn't show up in the cost, I don't really care what value zi has. I just choose something to make this an equality. Any questions on this? Yes?
Just a question on like the notation. So if you have ai1, ain, but then you have it greater than bi, do you mean b as the vector or bi as
No, the ith component of b. So we're looking at the ith row of our matrix dotted with the vector x is going to equal, was going to be greater than the ith element of the vector b. Yes?
Sorry, where are we putting zi?
Well, we're adding another variable z. So we're actually augmenting the matrix A. We're going from our matrix A to an expanded matrix A. I'm sorry, yes, the expanded matrix A. Where we're going to add some stuff in here now. So for each row, we're going to now make the matrix A a little bit bigger. And we're going to make our vector x bigger. X is going to go to like x and then some z's over here. And so it's not necessarily the same matrix as before. It's not necessarily the same variables as before. And that's where there's a cost. Because we now have more variables to analyze. It might be better to write a program that takes into account greater than or less than. But it would be really painful when we're doing the theoretical analysis to have to keep track of what are all the different relations. It's nice if I know I always have an equality. So when we're trying to prove things, it's tremendously useful to have things in a standard form. So that's the whole theory of formulating the problem. The next thing, which we'll talk about in the next class, is how do you actually solve it? What do the solutions look like? Where do you find them? What I wanted to end with at the end of today is talk a little bit about one of the big notations in mathematics. So you were talking about the word canonical. I want to talk about the word fundamental. How many fundamental theorems have you heard in your life? What do we know? Fundamental theorem of calculus, arithmetic, algebra. Sometimes people talk about the fundamental theorem of linear algebra. I think that's pretentious. I don't think the theorem rises to the same level. In probability, what do we have? Yeah, I mean, I would almost consider that a fundamental theorem. It's not called fundamental, it's pronounced differently, but it's still essentially the same. So I want to talk briefly about the fundamental theorem of calculus and how you would prove it. So how many of you have seen a proof of the fundamental theorem of calculus? Not every hand is up. How many of you could prove the fundamental theorem of calculus? Right. There are certain things that need to be checked before you are allowed to graduate. Seeing a proof of the fundamental theorem of calculus is one of them. Right? I did not let somebody graduate once until she had seen the movie Star Wars. She was into computer science and special effects. And if this is what you want to do, you need to see Star Wars. So proof of the fundamental theorem of calculus. And so this is a good way to just review some analysis and some stuff you should have seen. So the integral from a to b f of x dx is f of b minus f of a, where the derivative of big F is little f, so it's not unique, and the left-hand side is the area from a to b under f of x. If you do not say the word area, it may be worse than wearing a Yankee hat to class, okay? If you really want to get me upset, forget to say area. If you do that, if you don't say area, this is the fundamental definition of calculus, right? The content is that this left-hand side is the area under the curve from a to b. If you don't say area, well, is this just how you're defining the antiderivative? In which case, there's no real meat, there's no real content. So what goes on, I'll assume we're on the interval 0, 1 for simplicity. And let's just, chop it up. Here's xn, here, well, sorry, here's xk, here's xk plus 1. And I'm going to have each one of these of size 1 over n. And on each one of these, what we're going to do is we're going to find the upper and the lower sums. And we're going to show the upper and the lower sums converge to a common value. And the common value is the area under the curve. All right. We have 10 minutes to prove the fundamental theorem of calculus. I think we can do this. And again, this will be a good way to review a lot of our techniques. So the upper sum is going to be the sum, k goes from 0 to n minus 1, fun times 1 over n. And so f of un is going to be where the function is largest on the interval. The lower sum will be the sum, k goes from 0 to n, of f of ln, 1 over n. And so here's xk, oh sorry, these should be keys. Xk plus 1. And if I had something like this point here would be where my function is smallest. This point here would be where my function is largest. Clearly the upper sum can't be smaller than the lower sum. Yes?
Why is the upper sum going to n minus 1 and the lower sum going to n?
Sorry. Okay. And so we want to show 0 less than or equal to upper sum minus lower sum. And that's going to be the sum, k goes from 0 to n minus 1, of f of un minus f of ln times 1 over n. So we can review summation notation a little bit. How many of you have taken real analysis? If you've taken real analysis, now you can start to say, I have a continuous function on a closed bounded compact interval, therefore, by uniform continuity, blah, 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 blah. If you haven't taken real analysis, assume the function is differentiable. So if we assume f is differentiable, this is equal to 1 over n, the sum k goes from 0 to n, f prime at some intermediate point times un minus ln. So this is the mean value theorem. Anybody fans of, yes?
Why is it going to n and not
Because because I hate this. And so I will constantly be dropping the minus ones. How many of you have ever seen the TV show Friends? What is every episode but 1 or 2 titled? The one with. So this is lecture is the one with the mean value theorem. When in doubt, use the mean value theorem. This is a chance to just advocate for the mean value theorem, how much it shows. It's the poor person's Taylor series. So the mean value theorem tells us this difference here is f prime at some intermediate point. And so now we get the upper value minus the lower value is less than or equal to 1 over n. Then I'll take the maximum of f prime of x in absolute value. And now how big is un minus ln? Maximum, how big is that? 1 over n. And then I have a sum, k goes from 0 to n minus 1, so I get an n from that. And what's nice is, if the first derivative is bounded, then I have a 1 over n squared or 1 over n. This goes to 0 if f prime is bounded. So I don't need to be assuming things such as the first derivative exists. I don't need to assume that the function is bounded. But if I do, I can prove this in 10 minutes and not have to have all these real analysis machineries. So let's just do that. So this proves that the upper and the lower sums converge. Wonderful. So if I want to find the area under the curve, I just look at the upper and the lower sums. Now I want to show that they converge to the antiderivative. So what theorem do you think we should use? Yeah, exactly, the mean value theorem. This is the one with the mean value theorem. So what is 3 minus 2 plus 7 minus 3 plus 11 minus 7 plus 191 minus 11 plus 2019 minus 191? This is equal to? So what you notice is, just screw it. Don't add it linearly, row by row by row. It's a telescoping sum. If you do the calculations a different way, it's much faster. Oh, that might be relevant then in an operations research class. Okay, right? This is an efficient way to analyze things. The sum is much easier to do like this. And it just becomes 2019 minus 2. This is the key idea in the proof of the fundamental theorem of calculus. What we're going to do is we need to apply the mean value theorem to a good function. We applied it first to little f. This is priming you. What should we apply it to now? Big F. So look at the sum. K goes from 0 to n minus 1. Big F of xk plus 1 minus big F of xk. And when you telescope this, this is just big F of 1 minus big F of 0. Everything else cancels. By the mean value theorem, this is the sum. K goes from 0 to n minus 1. What's the derivative of big F? Little f at some intermediate point. So let's call it xk star times, what's the difference between xk plus 1 and xk? That's just 1 over n. Notice how similar this is to the upper and the lower sums. This over here is at most f of uk, and it's at least f of lk. So this is going to be greater than or equal to the lower sum, and less than or equal to the upper sum. And now we use the squeeze theorem, right? This lives between the lower sum and the upper sum, and as n goes to infinity, what do the lower and the upper sums converge to? The same thing. Be more specific. What same thing? The area. So because the upper and the lower sums converge to the area, anything in between is squeezed to converge to that area. Now what's really nice, does this sum depend on n? Does this sum change as I change n? What does this sum always equal? So this sum is the same as this sum. What does this sum always equal? I'm sorry?
F1 minus
It's right, it telescopes. We have f1 minus f0 plus f2 minus f1 plus I'll write that way. We have f of x1 minus f of x0 plus f of x2 minus f of x1 plus f of x3 minus f of x2. These cancel when you telescope, and it's going to just equal f of xn minus f of x0. x0 is just 0, xn is just 1. So what we've seen is f1 minus f0 is always between the upper and the lower sums. The upper and the lower sums converge to the true area. Because this doesn't change, and it always lives between, what is the only thing possible for f of 1 minus f of 0? It has to be the true area. And that is the proof of the fundamental theorem of calculus. Not even 10 minutes. Now, we assumed a couple of things. We assumed the function f was differentiable. We assumed it was bounded. Who cares? Okay? You can go through great lengths and say, what is the most general form possible where you can get the fundamental theorem of calculus? A tremendous amount is applicable here. Most of the nice functions you look at are going to be differentiable, and the derivatives will be bounded. So this is not a huge deal. But it's good to get a sense of, well, what do we need to push things further? Where did we use this stuff? We really needed this to prove that the upper and the lower sums converge. It is not necessarily the case that the upper and the lower sums converge monotonically. Maybe they oscillate a little bit. Maybe the upper sum gets a little bit larger than smaller, but heading downward. And this is where sometimes it's nice to do things in a good way. To make things nicer, you don't go from n equals 5 to n equals 6 to n equals 7 to n equals 8. You go from 2 to 4 to 8 to 16 to 32. We've done this before. And if you do it like that, it's called a refinement. So we start off with 0, 1. Then we put in the 0.1/2. Then we put in 1/4 and 3/4. Then we put in the 8s. And when you do it like that, then you're going to have a very nice sequence for your upper and lower sums. Because then each one is going to be living entirely in the level above. And you're just splitting everything in half. Otherwise, if you go from breaking things into fourths to breaking things into fifths, where things are largest to smallest could have a lot of problems. So there's a lot of really good lessons we can extract from this proof of the fundamental theorem of calculus. When we are proving something theoretically, at the end of the day, we don't necessarily care about how we're doing these calculations. It might make things a little bit easier to do them in a certain way. If we do things with powers of 2, the calculations are a lot easier. A lot of times when we program things, we actually like to program things with powers of 2. This is the matrices that are powers of 2. Strassen is perfectly set up to use. If you don't always have powers of 2, there are still things you can do. But if you have your freedom, I would much rather do 1,024 data points than 1,000 data points. Okay. Any other questions on what we've done up till now? All right, so this is a good place to start. We will have another general lecture on Friday, and then on Monday we will talk about mental harmony.